can start, let other people join. So welcome everyone. This is NOC 26W168 NPTEL tutorial session on semiconductor devices and circuits. The course instructor is Professor Sanjiv Sambandan from IISc. I am Debashish from IIT Kanpur. So as you know, this course goes live, this tutorial session goes live every week from 3 to 5 on each Saturday. So this is week 2. Before we start, any questions from last week? By the way, am I audible?
Yes, sir. Yes, audible.
Okay. So if no questions, so I think we can start. Let me see. It is still charging. Okay, anyway, we can start. So this is week 2. So let's begin. So the question says that a wave function is given by this, some conditions are given. Then they are asking us to find out the value of this A, the amplitude of the wave function, right? So this, for this kind of problems, one thing is for sure that you need to invoke normalization integral, okay? So whenever there is a question regarding finding out the amplitude of the wave function, you can go ahead with, given that proper boundary conditions are known to you, you can go ahead and draw the potential profile and then just do the integration, right? That is what we are going to do here. So the well is like this. So x equal to 0, x equal to L. So why we are drawing it like a well or a potential well, or more precisely infinite potential well? Because we know that in these two regions the wave function is 0, beyond this and beyond this. So that means a well-known case for us is the infinite potential particle inside a infinite potential well, right? And then we have some kind of wave function inside this. So what kind of wave function inside this? So inside this we have psi equal to a square root 30 x L minus x. So how do it look like? So at x, if put x equal to 0, so I'll have 0. Put x equal to L, again I'll have 0. How about L by 2? Put x equal to L by 2. So I'll have some amplitude, right? Let's say L by 2 is giving me this. So one L by 2 is coming from here, another L by 2 is coming from here. So that will lead to L square by 4 square root 30. Now take any point between this, you will see that it will construct, more or less construct something like this. The wave function will be like this. Okay. It is good to have a visual representation of the wave function. Fine. Now what we are telling, that the normalization integral, that means area under this curve from 0 to L is 1. So that is what we have discussed last time, right? So from normalization condition or normalization integral, we know that what is the normalization condition? This, right? Equal to 1. So now according to my boundary condition, my integration limit I can change from 0 to L, and this psi star is the complex conjugate of the surface, this wave function, right? So if my psi is a real valued function, as it seems from the question, because x and L are both real valued, right? And A is the amplitude. So it will simply be your psi square dx. So in another sense, it will be a square 30 and then x square, then x square minus 2lx plus L square dx equal to 1. Yes, fine. So then moving on with the integration, a square 30. So here I'll have x raised to 4. So that will give me x raised to 5 by 5. Then minus 2l. I'll have x cube. So that will give me x raised to 4 by 4. Then I'll have x square. So that will give me x cube by 3. So I have a square 30, and from here I'll have L raised to 5 minus L raised to 5 by 2 plus L raised to 5 by 3. So this will be 6 minus 15 plus 10 L raised to 5. So basically your A will be L raised to minus 5 and square root of that. That will be basically L raised to minus 5 over 2, right? So this one will be your correct answer. Fine. So the basic crux of this problem was to identify that this profile essentially emulates your infinite potential well problem, right? Once you know that, then it is just a simple integration. Fine. I hope there should not be any doubt in this, or if there, you can ask. Anyway, so let's move on. Move on. So another question, right? So an electron is bound in an infinite 1D potential well. So again, infinite potential well problem. So let's try to solve that. So infinite potential well, we draw it like this. So by the way, what is the when I am drawing till this much, what is the y-axis? The y-axis is your energy, right? And in this picture, the y-axis, the blue one is energy. However, this is your wave function, this green one, right? So if you see plots, let's say, let me just draw. Let's say I'll just draw this. Okay, so okay, let me just draw a half circle. Fine. So I will draw, so I will mention this is my F. Okay, and let's say this is X. So on the same line, I can draw the derivative as well, but I will have a different scale for that. Let's say F dash. How will my F dash look like? So at this point, my F dash is 0. At this point, my F dash is negative infinity. Okay, so it will simply look like this, right? This is your F dash, the red plot. So I can plot multiple quantities or variables in the same 2D plot. Albeit it should be differentiated by some, let's say one I draw with a solid line, another one I draw with a broken line, or some different colors, right? Different colors, we call it legends, right? These two differentiation between these two plots are called legends anyway. So this is just a circle, half circle, and this is the derivative of that circle. Fine. Are you following what how the derivative has come about? Yeah. So basically here your slope is 0. In this point your slope is 0, right? In this point your slope is positive infinity because it is a circle, and in this point your slope is negative infinity, right? And it will change like this. If you if you get the circle equation and then plot, it will give you the similar answer. Fine. Anyway, so let's move on. So similarly, for this, this is a infinite 1D potential well. 1D means my this axis space I am considering in one dimension only. That means my particle can move either this way or this way. Okay. And if it can move this way, so this is my 2D, and if it is can move, if it can move up and down of the plane of the paper, so it becomes a 3D. So it is just a representation. Fine. Okay. So what is mentioned in the question that potential well of width 7.3 nanometer. That means the width of this potential well is 7.3 nanometer, and then along the axis, along the x-axis, okay, the system is at state n3. Okay, so system is at state n equals to 3. The probability of finding the electron per nanometer length at x equal to 3 nanometer. Okay, so let me put this is 0 and this point is x equal to 7.3. Let's say the unit is nanometer. So they are asking us to find the probability at some point here, right? At x equal to 0.3 when the system state is n equal to 3. What does that mean? We have seen that inside an 1D potential, infinite potential well, the electron can occupy certain specific energy levels, right? This was the last problem of the previous week, that my wave number becomes quantized, and that leads to my k becomes quantized, and that leads to my energy becomes quantized. Basically it depends on the value of n, and how that n value was coming about. It was coming from the boundary condition of psi, right? You remember sign of uh, L x L sine of pi L is equal to 0. So from that condition, sine of KL is equal to 0. From that condition, K turned out to be n pi by L, right? So if you remember, we have solved the Schrodinger equation. I'll save myself from solving it again. And if you remember, the equation was of the form square root 2 by L, then sine of n pi by L times x. This was the solution of the Schrodinger equation in an 1D potential well. Fine. First, we use the boundary conditions at these two locations, which is 0. Infinite potential well means this will become 0. And then I'll just find out this value of K, and then after, with the normalization integration, I found the value of A, right? These were the steps. So now the question is, we need to find out the probability, right? What is probability? That also we have discussed. So this quantity psi star psi gives you psi star psi dx, let's say. This quantity gives you probability of finding a particle in a uh, as it is 1D, so it will not be volume, it will not be area. We call it as a line width, right? As a line width of dx. Fine. So what is asked in the question? It is asked that per unit length. So that means probability of finding the electron per unit length will become simply psi star psi. Same thing, but this time per unit length. Okay. So I just need to find out my psi star psi. So what will be my psi star psi? So this equation, is it real or imaginary? Anyone? You are not audible. Real, yeah. So it is real, right? So simply it will be the square of this term. So that will be 2 by L sine square n pi L times x. Fine. So this quantity psi square psi at x equal to, what do I get? To 0.3 nanometer. It is given in the question, right? And n equal to 3. I need to compute. So it will be 2 by L is my 7.3. Let's keep the per unit nanometer out. That is coming from the 7.3 nanometer. Then I'll have my sine square, because sine of something as is unitless, right? So n is my 3, pi L is 7.3 nanometer times 0.3 nanometer. Nanometer gets cancelled because my length is normalized here. So this will be my answer. So if you just use your calculator and find it out, you will see it comes out to be 0.039 per nanometer. Fine. So my probability of finding the electron is nothing but 0.039. per nanometer. Fine. So this is how you solve it for probability density. In this case, particularly probability, because density part is coming from this per unit length part, right? So this quantity is probability density. Okay, but this entire thing is probability. So please understand the difference between these two. Right? Okay. So if that is done, so let's move on to the next one. Okay. So let's read the question carefully. Electrons are accelerated through an electric potential V and then fall on a pair of slits that have a separation of this. Okay. Let us try to construct the apparatus what they might be using. So this is similar to your Young's double slit experiment, right? So it is mentioned that, let's say I have a electron gun here. Okay, let's say I have an electron gun which is shooting electrons. Fine. And then I have a double slit like this. Okay, and it is mentioned that electrons are further accelerated, right? So how can electron, let's say electron is getting emitted this way. So how can you accelerate one electron? You have to apply some attractive force, right? That by what thing electron gets attracted? Electron being a negative charge, it gets attracted to positive voltages, right? Or higher potential. So what they have done, they have added a battery here, let's say of voltage V or potential V, right? So the plate, let's say this is this we called it, let's say plate. So this plate is V potential higher than the position from where the electrons are getting emitted from the electron guns. So electron will get attracted towards this because my electric field lines are in this direction, right? So that will accelerate my electrons. Fine. And it is also mentioned that the spacing here is 100 nanometer. Okay. Then let's proceed. The resultant interference pattern indicates that the electrons have a wavelength of 1 nanometer. Fine. So resultant interference pattern, where do we see it? Let's say I have some kind of zinc sulfide or whatever it is, some kind of screen here. Let's say this is my screen where I am seeing the interference pattern. So electrons are getting shooted in all the directions. So electrons, as you know, this is the proving experiment for the wave particle duality. So one wave will be coming out of this slit, another wave will be coming out of this slit, and they will interfere, right? Interfere means they will, as you have seen in the last session, that interference means nothing but addition of the waves, right? And then it will create some interference pattern. Fine. And what it is mentioned, that the interference, from the interference pattern, you found out that the wavelength of the electrons are 1 nanometer. Okay. So is the setup clear? So if it is uh, this way, then the question they are asking us, what is the value of the accelerating electric potential V? That means they want us to find out first what is this voltage. How do we find out that? Any idea? So what are the known quantities for us? Anyone?
We know lambda h and so we can use de Broglie's
Can you
relation.
please speak a little closer to the microphone?
So we can
Yeah,
use de Broglie's relation
we can use de Broglie's relation. Fine.
uh, to
And
find the
then
voltage V.
how do you do that? Let's say
Lambda,
my de Broglie's relation is lambda equals to h by p, right?
yeah, yes.
From this, how can I find out my voltage?
Uh, P is equal to, we can substitute, no, sir, MP voltage.
Please guide us. Let us try to see how do you do that. What are you saying? Can you repeat?
Yeah, lambda is equal to h by square root of 2 MeV.
Okay, so you mean to say lambda is equal to h by square root 2me, right? And
Yeah,
this E being
yeah,
kinetic energy of the electron, right?
yeah, yes, sir.
Kinetic energy of electron, because for those who are not getting it, lambda equals to basically half mv square, right? So basically half m square v square by m, and that is basically p square by 2m. So your p turns out to be square root 2me. This is only possible when my this is a kinetic energy or half mv square, right? Yeah, then
Then we can substitute for lambda. Lambda is given as 1.
so let's say lambda is, we have received lambda equals to h by square root 2me. Okay, let us substitute for lambda. Lambda is what?
1 nanometer.
Okay, so lambda, let's say 1 nanometer, 10 raised to minus 9 meters,
Then we
and
know H.
h, let's say 6.626 into 10 raised to minus 34. M we have, m is 9.11 into 10 raised to minus 31. What about E?
E is what we need to find, right, sir?
Sorry,
E is what we need to find, sir.
how do you find E? E is the kinetic energy, right?
Yeah.
How do you find kinetic energy? Yeah, you are on the right track. Just think a
Yes.
little bit more.
Yeah. So after finding E from this, what we substituted, from that we can find the potential.
Yeah, but how do we substitute E?
E we can find out from here now, sir. Like all the other parameters are known, only E is unknown. So we can find from this
Okay,
substitute.
so let's say you want to find out E, right?
Yes,
So let's find out E. So E will be how much?
it will be like h square by 2m lambda square.
Okay, let's just go about it. So 10 raised to minus 9 divide by so 6.626 into 10 raised to minus 34 divided by 10 raised to minus 9, that square, right? That square, then divided by 2 divided by 9.11 divided by 10 raised to minus 31. So it is coming around 2.4 into 10 raised to minus 19 joule, right?
Yes.
Then what?
Then this joule we need to convert to electron volt, I
Why?
think.
Why will we convert joule into electron volt? That is just unit conversion, right? I
Yeah,
how
yes.
can how come my kinetic energy be in electron volt? That is if I you do you understand what electron volt represents? So your suggestion is to, let's say, convert it to, let's first convert it to electron volt. Okay, divide by 1.602 divide by 10 raised to minus 19. Fine. So this will become 1.504 electron volt. Fine. So what will be the voltage from this? I'll just omit the electron. That was the plan.
Yes.
But my question is, why should I do that? Means it is just not unit conversion, right? Understand that whatever equation you are using is E is kinetic energy, right?
Yes.
But whenever, let's say, I have some potential difference and a charge is moving. So in a potential, if there is a charge, what kind of energy it will have?
To be kinetic energy.
No, it will have potential energy, right? You understand the term potent, in potential we have some charge.
Potential. Yeah. Yes.
So it will be potential energy, right?
Yes.
Then the question is, how come this potential energy is getting converted to kinetic energy? You see where I'm getting into.
Yeah. Yes. The electrons are getting charged. No, it is accelerating. So this potential is converting to kinetic.
So this potential energy, that is, so basically what is happening? So this guy is giving me potential energy, right?
Yes.
And this is making the electrons to accelerate. And once electron starts accelerating, let's say with some varying velocity at any time instant t, any time instant v, so it will have, it is basically doing what? It is converting its potential energy that it has received from the battery to kinetic energy and getting passing through these slits and getting interfered, right? So there is a energy transfer is going on, right?
Yes.
From potential energy to kinetic energy. So that part I wanted to know that whether you are understanding this or not. Fine.
Okay, sir.
So as PE is getting converted to kinetic energy for the electrons, so I can write E equals to QV, right? And from this, I can directly write my voltage to be 1.5 volt, approximately 1.5 volt. Okay.
Yes, sir.
So, okay, voltage I have found out. So this part of the question is done. So what is the value of the accelerating electric potential V? Let me just add a page. Yeah. Then the next question is, after passing through the slits, what is the minimum spread in electrons momentum in the direction parallel to the plane of the slits and perpendicular to the average path of the electrons, right? How do you do that? So what they want us to find out. So this is my part 1. Say they want us to find out spread in electron momentum, that is delta P. How do we find that out? Any idea? Have you heard of this relation? Have you seen this somewhere? I think somebody is writing the answers. Heisenberg's uncertainty. What does this mean? Is this the only form of Heisenberg's uncertainty principle? So what does Heisenberg's uncertainty principle mean? Anyone? We have been reading this since plus 2, right? This means that, yeah, please go ahead.
So it is impossible to know both the position and momentum of a particle at the same time.
Not quite so, very close, but not exactly. So it is not possible to know the exact location of any particle and its momentum to the infinite precision, right? That means there will be some error. Fine. So what does this delta x means? Delta x is basically, let's say this is a space, okay? And my particle is sitting here. So let's say this particle is at x equal to x naught. Fine. And the momentum of it is, let's say, p equal to p naught. Then what Heisenberg's uncertainty principle states is that if I want to measure the position of the particle, there will be some error associated with it. This error is your delta x, right? And then, so there will be a possibility where this is at x0 plus delta x, let's say, considering both sided, otherwise it will be plus minus delta x. Similarly, the position of it is, let's say, p0 plus delta p. Okay, so I cannot measure exactly. If I can measure the position exactly, that means if my delta x is equal to 0, fine. So from this inequality, you note that if delta x equal to 0, what will lead my delta p be? Delta p be infinity, right? Because h bar is a constant, non-zero constant. Constant by 0 is equal to your infinity, right? So if I know my position precisely, or vice versa, if I know the momentum precisely, then I cannot know the other quantity. Fine.
Yeah. Okay, sir.
So how will we use that in our case? Let's say I am observing this particular interference pattern. Fine. Because this is what I can measure, the property of the interference pattern. This is what I can measure, or this is my observable, right? So let's say this entire stuff, this let's say this entire stuff is in a different room altogether, and you are access to only the interference pattern. Fine. Then let's take a point. Let's take this point. By looking at this point, can you tell me, or can anyone tell, if this contribution is from the electron coming from slit 1 or slit 2? Do you see what I mean? I am observing the interference pattern at any point, let's say at any crest or any trough, or any high or any low of the interference pattern. Can I just looking at that tell that whether it is being caused by the first slit or the second slit, or basically the electrons coming from the first slit or the second slit?
No, sir. I can't say exactly.
It is not possible, right? We can just guess. If it is more closer to the upper half of the screen, we can say that it is more likely that it is coming from the slit 1, right? So we cannot know that exactly. Fine. So from this analogy, can you tell me what is the delta x here? The uncertainty or the very standard deviation of the position. What is my delta value of delta x here? De,
That is the
yeah,
wavelength one, maybe.
no, it's not the wavelength, right? See, I am standing here, right? What is my ambiguity? My ambiguity is I do not know if it is coming from this or this. You see, if it is coming from this slit or this slit. So what will be my delta x? My delta x is nothing but the distance between the slits. That is the same thing. Let's say at this point I have one slit and this point I have another slit. I have an ambiguity between these 2 points, right? I do not know it is if it is coming from slit 1 or slit 2, right? So my delta x is this one. What is this? 100 nanometer. I will take a pause here for you to just take this in and understand this very carefully, please. Do you see what I mean? Why delta x should be the distance between the slits? Because this can come from any of these two locations, right? And what I want to find out, what is my ambiguity? See, before this, I do not have a problem. I know it has to, the electron has to come from anywhere from this slit or this slit. So the maximum delta x possible for me to consider is 100 nanometer. Is it clear?
Yeah, I see.
So if that is clear, then it becomes a simple task to find out delta P, because delta P will be greater than h bar by 2 delta x, right? So h bar by 2 delta x is 6.626 into 10 raised to minus 34 joule second divided by 2 pi, because it is reduced Planck's constant h bar, times 2 times 100 nanometer, right? So if you can solve, so you will have 6.626 into 10 raised to minus 34 divided by 4 pi divided by 100 divided by 10 raised to minus 9, right? So you will have 5.27 into 10 raised to minus 28. Okay, so your this delta P has to be greater than 5.27 into 10 raised to minus 28 kilogram meter per second. That is momentum, right? So this is one answer. This is another answer. So do we have any option for that? So C is a viable option, but again we do not know it for sure that my delta P will be twice that of what is calculated, right? It is greater than 5.28, that is for sure, right? So both of C and D are viable options. Is the problem clear? So everything is written in the question. You have to just uh, read the question very carefully. Fine. Construct each part individually, understand the physics behind it, and then if you know the laws, it will just be your algebraic manipulation to solve it. Fine. Okay. So let's move ahead. Okay. The value of the wave function of a particle at state n is given by this. Fine. So it is given that my psi of x is square root 3 cos 2 pi by a x for mod x less than equal to a by 2 and 0 otherwise. So again, it means that I have an infinite potential well, and this is my x equal to 0. This is x equal to minus a by 2. This is x equal to a by 2. Fine. And in this locations, it is mentioned that psi is 0. Fine. Then what is the average momentum of the particle at state n? How do we find out the average momentum? So let's say they want us to find out the px average. So this is the notation for expectation value or the average value. Fine. How do we do that? We integrate psi star dot, this is my momentum operator operating on wave function or eigenfunction psi dx. Okay, this is how we find the average value of any function. The operator part I have discussed in last session, so you can go and check about it. How from a equation of wave we come about with the operators. We have discussed momentum operator, kinetic energy, potential energy, total energy, time varying total energy, and position operators, right? So this is the equation that you will be using. Fine. So this is basically the complex conjugate of the wave function. This is an quantum mechanical operator operating on an eigenfunction, that is my wave function. Fine. So how will you do it? From our equation, we know it is from valid only from minus a by 2 to a by 2, otherwise my psi star will be 0. Then it will be psi star, that is only psi in our case, cos 2 pi by a x times what was my momentum operator, by the way? Can anyone remember? Momentum operator was h bar by I del x, right? This was my momentum operator. If you have any doubt, please go revisit the lectures or revisit the recording of the previous session that we have done on last Saturday. So I will have h bar by I del x of the wave function, that is square root 3 cos 2 pi by a x and then dx. Fine. So let's solve it. So let's bring out the constant outside first. So there is a square root. Okay. So there is a square root 3. So 3 h bar by I minus a by 2. I'll have cos 2 pi by ax. Then I'll have a minus sine 2 pi by ax, and then again 2 pi by a outside, right? Please correct me if I'm doing any maths wrong, okay? So I'll have what? 3 I h bar. So let's say 6 by, let's take it 3 by a pi, okay? Then I'll have minus a by 2, 2 sine 2 pi by ax cos 2 pi by ax. Then I'll have 3 I h bar pi divided by a minus a by 2 to a by 2 sine 4 pi by ax dx. So I'll have minus 3 I h bar pi by a times a by 4 pi, and this will be cos 4 pi by ax a by 2 minus a by 2, right? This gets cancelled, so minus 3 I h bar by 4. So this will become cos a by 2 becomes 2 pi minus cos minus 2 pi. So this is 1, this is also 1. So this entire stuff will result us in 0, right? So what do I see? I see that delta px, average value of the momentum, is 0. Now, can you interpret this result? What does average value of the momentum 0 means? Is it classically possible? So, my question is, from classical mechanics, we know that momentum is conserved, right? But here I am seeing that my momentum is 0 from quantum mechanics. What does this mean? How come momentum, average value of momentum be 0? We know that for elastic collisions, m1 v1 equal to m2 v2, right? That is your linear momentum conservation. But how come your momentum be 0? Can you give me any scenario in which momentum you see to be 0? See, this is simple to think, right? Why I am saying that? So momentum average value means what? Average value of M and Vx, right? M is the, let's say, the mass of the electron, which is not zero, right? So that means M will come outside and Vx will be zero. So my average value of the velocity of the electron is zero. So can we have this situation? Have you heard of the concept of random thermal motion? Anyone? What does random thermal motion mean? So please try to interact so that it will be better for you to learn, right? You may be wrong, that is completely fine. Random thermal motion means, let's say you are uh, at a T equal to not zero, non-zero temperature, right? And if you have electrons or free carriers, how will they go about? They just take any random path, right, and move accordingly. We'll see when we'll discuss mobility, we'll see how this random thermal motion means. Random thermal motion means there is a very good analogy that Professor Karmalkar from IIT Madras has given in his lectures, that in a sweet shop, when the sweet box is open, you see that the motion of flies. Have you seen that the motion of flies roaming around the sweet box? Have any one of you seen flies roaming around a sweet box if it is open in a sweet shop? Come on, this you must have seen, right? This is not electrons. So that motion is comparable to the motion of electron if the material or the device is kept in thermal equilibrium. So in thermal equilibrium, it does not mean that the electron are stagnant, right? Electrons are never stagnant. Once you have sufficient energy, thermal energy or whatever form of energy, maybe light energy or whatever not, so your electrons gets from valence band to the conduction band. Once the electrons goes to the conduction band, it becomes free carriers, right? It means that electrons are roaming around the material or the crystal, and you cannot say that this electron is particularly belonging to this particular atom. Fine, that is the meaning of free carriers. It is free of any particular potential energy of the atom. Fine. So those electrons roam around freely around the crystal. They get bumped from many of the particles we call scatterers, and they follow this kind of random thermal motion. So what happens in random thermal motion is that the average velocity or the average thermal velocity of the electrons remain zero, right? That means if an electron is moving from left to right, in the entire crystal, some other electron will move from right to left by the equal amount. Okay. So this way the overall motion of the macroscopic motion of the uh, electrons in a crystal remains zero, right? So this is what random thermal velocity or average velocity being zero means. Okay. So in those kind of conditions, your momentum also, because mass is for now mass we consider as a scalar. We will see that effective mass is not a scalar; it becomes a tensor. So this mass being scalar, you can take it out of the expectation or the average symbol, and your velocity can be zero. So your momentum, average value of the momentum can be zero, right? So this is a distinction from your classical mechanics, fine. Where you have a, if you have a particular velocity, you then will have this, momentum has to be conserved in any elastic collision. For example, in your snooker or billiard, if you have seen, or pool, if you have played, one the white ball, cue ball is hitting any red or colored numbered balls. So if you play the shot called stun, so the white ball gets stopped, and from with equal velocity, the other ball moves, right? Provided their mass are same. Anyway, so let's move on. Okay, so this is a question. Please pay attention. So last time we had stipulated some conditions on the properties of psi, right? Properties of psi. What did we note? That psi has to be continuous, single valued, well behaved, differentiable, and so on. And same we have stated for psi star also. Psi star also has to be continuous, well behaved, right? But we have said that the second condition can get violated in certain cases. This particular question is one of such cases. Okay, so please pay attention. So it is mentioned that consider a particle of mass m moving in a one-dimensional potential well like this. Oh, for x, okay, let me just remove this. Yeah. So and v equal to this. Basically, this is an infinite potential well, right? That means if I draw the potential well, so this is infinity, and this is x equal to minus a. This is x equal to a, fine, and somewhere here is x equal to 0. The value of a, the question is that we need to find out the value of a for which the ground state energy of the system vanishes. Fine. So what is the potential profile? Earlier, so far what we have noted is that between inside the potential well, the potential energy is 0, right? But in this case, that is not the case. The potential profile in this case is something like this. There is another delta function sitting at x equal to 0. Okay, that is here your psi is equal to, or v is equal to A times delta x. Okay, that means it has value only at x equal to 0 because delta function is not shifted by any space location, right? So now we need to find out the first we need to solve the Schrodinger equation to find out the wave function, and from that we need to find out the this value of A. And what is this value of A? A is the value of this potential delta potential that is sitting at a at particular location. So the question now is, uh, does it emulate any particular practical scenario? How can we have a delta infinite potential? Or for that matter, uh, where do we see delta functions in real life? That will be more valuable question. Anyone? Where do we see delta functions in real life? Let's say I have a metal cube. Okay. Let's say I have a metal cube. Fine. And now we are only concerned about the 2D picture of it. So I am drawing this uh, front view as this. Okay. Now let's say this metal cube is charged with a charge Q. Where will this charge be located? In a metal cube, if the cube is charged with a charge, let's say plus Q, let's say plus Q coulomb, where in a space or in the position domain, where will the charges be located? And let's say about what about a metal sphere? If it is charged with plus Q, where are the charges located? Come on, this is very trivial stuff, right? In a metal sphere, where are the charges located? Anyone? Will it be distributed across the volume? Can anyone unmute and tell?
The outer surface.
At the outer surface, right?
Yeah, yes.
And why does it happen? The charges are equally distributed at the surface of the sphere. The same thing will happen to this also, the cube also. The charges will be located at the surface of the, so this is one surface, this is another surface, right? So similarly here also you will have charges, right?
sir.
Why does it happen so? Why does it happen so?
Uh, because of repulsion, it tries to move,
Because of
because of the repulsive force, it's trying to move far.
because metal is equipotential surface, right? One thing is that. Second thing is, what is the skin depth of metal? Can electromagnetic wave penetrate a metal? No, right? Skin depth of the metal is zero. And that is the same observation you find out from Gauss law as well. One is metal is equipotential surface. Second is skin depth is zero. What is the consequence of this? Have you ever noticed that when you are going up or down in a lift or in an escalator, in a lift for that matter, your mobile network gets lost? Have any one of you observed that?
Yeah, yes, sir.
That is the same reason, right? Because metal, the lift is made out of metal shield. So your phone electromagnetic wave, what you are transmitting, is not going to the outside environment. Everything is getting reflected back. And the same thing is happening from the outside world also. Fine. So this is because your metal skin depth is zero and metal acts as an ideal reflector of the electromagnetic wave or electric field or magnetic field. So that is why you cannot communicate while you are inside lift until unless there is some uh, other leakage path is present inside the lift, right? Similarly, note this point whenever you are doing any experiment. Some of you maybe in PhD will do some hands-on experiments. So you will see that your current levels and all are not going below, let's say, microampere or nanoampere, right? The primary reason for that, apart from the leakage currents, are your EMI/EMC. These are called electromagnetic interference and electromagnetic conduction. How to protect that or how to reduce that lowering of the, how to get more resolution in the current? Just cover the apparatus with aluminum foil, right? This kind of thing we called a Faraday cage. So cover the apparatus with aluminum foil and then you are essentially isolating the internal experimental setup with the outer world, right? So by doing Faraday caging, you are essentially prohibiting anything from light. Light is also an electromagnetic wave, right? Light or any other currents passing through one conductor, it will not get coupled into your experiment, right? It will not get inducing any charges so that current levels are not going down. This kind of things will not happen. You can even significantly increase the resolution of your experimental results and you can reduce the current levels by a lot, right? Your off will essentially seem off then. So these are some kind of hacks you should be aware of. All are coming from the same concept. Fine. Now, if this metal cube, I consider an interface in between, right? So how will my charges look like on this interface? My charges will be like this, right? There will be no charge inside, but there will be charges surrounding it. Let's say this is A, B, C, D, right? So this is any metal sheet cutting at the middle of the metal cube. Now let me make it more simplified. Let me just remove this particular parts. Okay. So I am just looking at this axis. Let's say this is my x-axis. So can you see that you have presence of charges only at a particular location of x? Let's say this is x equal to x naught, and let's say this particular location is x equal to x1, right? So how will you note the charge densities here? You will note it as x minus delta function, some constant, and also here you will note it as delta function with some constant. So this kind of, we call this sheet charges. So this kind of sheet charge, it can be represented by delta functions, right? So what is the point of sheet charge? That means over the space or over the x-axis, the concentration of this positive charges is in a single location or a single sheet, and the positive charge, whatever that may be constituting of either holes or any positive ions, the size of those are very small compared to the overall dimension of the device, so that you can consider it as a single point, right? So these are the cases where your this kind of delta function approximation comes into handy in your modeling devices and whatever not. Okay, so these are the motivation behind why these delta functions are necessary. It is not that delta function are not practically realizable. It is just that it is an mathematical approximation to make our life easier. Fine. So this is what is the scenario of the infinite potential well. So here it is mentioned psi is 0. Psi, it is not mentioned. Basically, my potential is infinity elsewhere, right? So that means this entire thing is infinity. So you know that in an infinite potential well, my wave function will become 0. Fine. Now, how many regions I need to operate in? I need to operate in these two regions. Let's say this is region 2, and let's say this is region 1. Okay, so I need to solve Schrodinger equation in these two regions. Fine. So let's start with region 1. So my Schrodinger equation, I'll write it in one dimension. Del square psi by del x square plus v psi equal to e psi. Fine. So what is my potential in region 1? In region 1, my potential is 0. So this goes to 0. And for what condition do I need to find out the value of A? When my ground state energy of the system also vanishes, right? That means I'll consider my energy, total energy that will give me my ground state energy for n equals to 1 is also 0, and I'll solve considering these two conditions. Okay, so if I do that, what will be my psi? So this will lead to del square psi by del x square equal to 0. That means del psi by del x equal to some constant, and again integrating that, I'll get, let's say, b1x plus c1. Okay, I think this is not difficult to follow. Similarly, in region 2 also, so this is psi 1, this is psi 2. So region 2 also I will have psi 2 equal to some this kind of waveform, right? Basically del square psi del x square equal to 0. So your del square psi by del x, del psi by del x will be some constant, and let's say this is b, and then your psi will be bx plus c, right? This is the form of the equation that we are using for both the cases. Now again what we'll do, we'll use the boundary condition. For us the boundary condition is that at these points my psi 1 equal to 0, here my psi 2 equal to 0, because my psi has to be continuous, right? So from that boundary condition, if my psi 1a is equal to b1a plus c1 is equal to 0, so that leads to c1 equals to minus b1a, right? Then my psi 1x becomes b1x plus c1 is my minus b1a, so that will be b1 x minus a. Okay, so this is my psi 1x, and about psi 2x, psi 2 minus a is equal to 0, that means b2 minus a plus c1 is equal to 0. Sorry, it should be c2. So my c2 is equal to ab2, right? Again putting this back into this equation, I get my psi 2x is equal to b2x plus ab2, so b2 times x plus a. Okay, so using the boundary conditions at the edges, I get psi 1x equal to b1 times x minus a, and psi 2x is equal to b2 times x plus a. Fine. Now we'll use the boundary condition at this point. So at x equal to 0, my psi 1x and psi 2x should be equal, right? So using continuity of psi of x at x equal to 0, we get psi 1 0 equal to psi 2 0, right? This gives me b1 minus a from this equal to b2a, right? So I get my b1 equal to minus b2. So these two conditions now I have. So let's assume this to be some quantity b. Okay, just for the simplification of our calculation. Fine. Now what we want to solve? We want to solve across this border. Schrodinger equation across this border. That means x equal to 0 minus to x equal to 0 plus. Okay, transitioning through x equal to 0. So now solving Schrodinger equation across x equal to 0. So I will have minus h bar square by 2m del square psi by del x square plus v of psi equal to e of psi. Fine. So in this case, as again I am calculating for zero ground state energy, I will make my E equal to 0. But this case, my V, I cannot make it 0, right? Because I have a delta function sitting there. So what I will do, I will have minus h bar square by 2m del square psi by del x square plus this function was a delta x, right? So a delta x psi of x is equal to 0. Okay. So now if I integrate it once, what I'll get? H bar square by 2m del psi by del x 0 plus 0 minus, and this entire thing 0 minus 0 plus delta x psi x dx equal to 0. I have just integrated the Poisson equation, right? Now what I'll do? So this is my h bar square by 2m. This is psi dash 0 plus minus psi dash 0 minus, and using the property of delta function, can you tell me what this integral boils down to be? Can I write this as psi of 0? Can I write that from the knowledge of your signal systems? This thing is also called shifting property, right? So from our equation, what is psi dash 1x? That is B1. What is psi 2 dash x? That is B2, right? For 0 plus, what should I use? For 0 plus means in this region, I have to use psi 1 dash x. Psi 1 dash x or psi 1 dash 0 gives me B1, and this will give me B2. Fine. And then a psi 0, what is my psi 0? So if I have psi 0 here, I'll have B1, B1 minus B1a, right? Psi 0 is same for both the cases. Psi 0 is same, right? I can have minus B1a or I can have B2a. Let me choose minus B1a. Then you will have, and what is the relation between, so B1 is B, B2 is minus B, so B is getting added. So, and then here it will be A minus A. So let's take it on the other side. A, B1 will be B and then A. So what will I have? Minus h bar square by M B equals to A B. So this will get cancelled. So my A turns out to be minus h bar square by m times a. So do you see? And what did I mean that these two are not psi dash is not continuous? So if you check psi dash, so in this region psi dash is equal to what? Psi dash is equal to b1, right? Sorry, this is region 2, so b2. B2 is minus b, and in this region psi dash is equal b is plus b. So psi dash is not continuous. It is only when there is a delta function or delta potential sitting inside the allowed area for electron to move, I will have this kind of situation that my psi dash is not continuous. This is not valid for delta potential profile. Okay. So whenever we are reading the properties and whatever not, we need to understand till the range at which it is applicable, right? So I think this is just maths, but you have to be very careful about the real life situations of delta function where you can model it with it, and also you need to know the properties of delta function, right? If you have forgotten, so please go and revisit your signal system courses. There is a book called Oppenheim, so you can read that, right? So anyway, so what is the option, by the way? Minus h bar square by ma. Yeah, this one, right? So these kind of questions you will get in your assignments. I am not sure what kind of questions are they are putting it this time, or in your exams as well, right? So that is why to understand these questions and solving them should be very important to you if you are willing to credit for this course. Anyway, so let's move on. Okay, so number of lattice points per unit cell in a body centered cubic lattice is, so there are a couple of terms. One is lattice point and then body centered cubic. So by the way, what does lattice means? Anyone? What is lattice? So historically speaking, if you put some block of woods, no, or wooden logs one top of another, okay. So these kind of structures are called lattice historically. So what are the inherent nature of the lattice? That it has to be some sort of periodic arrangement in a 2D space, at least in a 2D space. Even 1D we can have lattice, but let us understand it in 2D space, right? And these points, these are nothing but wooden logs, okay? Stacking on top of one row on top of another column like that, okay? And these points are called lattice points. From this analogy, in crystal, we call the periodic arrangement of the atoms lattice, crystal lattice, right? From this analogy, crystal lattice has come about. Okay, so what is crystal? There are three types of materials, right? Crystals, amorphous, and polycrystals. So basically, if I have three samples and let's say I have a random arrangement of the atoms, so this is my amorphous, amorphous, okay? And if I have periodic arrangement of atoms, then this guy is called crystal. All are solid, okay? Most of the times. And then if I have some well defined regions, let's say I have well symmetry, well order in this regions, but the order in one region does not match with the order in another region, then these are called polycrystals or polycrystalline materials. Okay, so these are the three types of materials. So in our case, we'll mostly use all of this, right? In a MOSFET, so if you have seen a MOSFET, this is the cross section of a MOSFET. So this is my source, this is my drain, this is gate, this is body. So let's say, let's make it n channel MOSFET. This is SiO2 and this is polysilicon, right? So this part is this polysilicon, polycrystalline. Okay, this particular guy is amorphous, SiO2, and remaining entire stuff is your crystal. Okay, so as the transport happens in the crystal only, so we will be more focused on the crystal, but nevertheless we need to have fair amount of idea about polycrystalline and amorphous, both kind of all kinds of materials. Okay, because all are used in your today's MOSFETs. Fine, so that is what lattice is. Okay, now what about this body centered cubic? So let's say you have in 3D the periodic arrangement of the atoms are such that the unit cell is a volume of the volume constituted by the atoms. If it can be repeated multiple times in any direction, it will constitute the overall crystal, right? So atoms basically sits on, if the atoms are sitting on these locations, these are called SC or simple cubic. Fine. There are other possibilities as well. For example, okay, let me just copy this. So there are other possibilities that apart from this, there is atoms sitting at the center of faces as well. Okay, so these are the how many faces are there in a cube? Six faces, right? So there will be additional six atoms. Okay, so these kind of structures, I'll show you in a moment how where you can see this kind of crystal structures more clearly, right? It is often not suggested that we should do it on pen and paper, but there are some 3D viewers. I'll share a link of one with you so that you can view it easily. Fine. These kind of things are called FCC or face centered cubic. Fine. Then there is another class in the cubic genre where you have these eight atoms sitting at the corner and one atom is sitting at the body diagonal, midpoint of the body diagonal. Body diagonal means opposite corners of the cube, and it is sitting at the center of the cube, right? So these are called BCC or body centered cubic. There can be total 14 types of unit cell, primitive unit cell structures. Okay, so now let me just share my screen. Okay, so is my screen visible? Can you see the sim tool crystal viewer?
Yes.
You can see, right?
Yes.
I'll share a link of this with you, but for the time being, just let me show you where you can see the correct way to look at crystals. This is a free source provided by Purdue University. They called it nanoHUB. So there are all sort of open source resources available in this, right? Whoever is doing research, you should go and check this out. Okay. So this is your crystal viewer. Okay. So let's start with a single simple cubic. Okay. So what are these? So we have rock salt. Rock salt is your simple cubic. Fine. Let's try to simulate. Let's try to go for the uh, textbook basis. Okay. So can you see? So
Yes.
this is your simple cubic structure. Fine. So now can you tell me how many for let's say This is for NaCl, right? Sodium chloride. So for sodium chloride, there are two types of atoms, okay, sitting alternatively on the each corner of the unit cell. These two types of atom together also called a basis. Fine. Now the question what I want to ask you is that this particular atom, let's say this particular atom, okay. So this particular atom, how much volume of this atom is inside this cube or this unit cell? What do you think? Basically, if I take, let's say this cube, okay, this inside atom, this inside one. So this atom is shared by how many cubes? This particular atom. Can you count?
8.
8 atoms, right? So, and due to the symmetry, so can I say that in one cube, the contribution of this atom is 1 over 8? You can see, right? This is one cube, upper one is one other cube. Similarly, here, bottom and top, here also same, there also same. So, total 8 cubes. So, this particular atom contribution to one particular cube is 1/8 of its volume. Is that clear? Fine. So now if I take a unit cell and tell you that combining sodium and chlorine atoms, how many atoms are there inside this unit cube? What will be your answer? So this atom has 1/8 contribution. This atom also has 1/8 contribution. Similarly, there are 8 atoms. So 8 into 1 by 8 will be 1, right? So for a simple cubic structure in an unit cell, how many atoms are there? There is only one atom. Okay. This is how we calculate it. And this distance, this from this to this is called what? Your lattice constant. Okay. Now let's look at a different structure. For example, let's look at uh, okay, body centered. Okay, let's look at body centered that we are discussing. See, this is what body centered looks like. Okay, so you have atoms sitting at each corner and you have a atom sitting at the center of the cube. Fine. So from this, how many atoms are there inside this one body centered cubic unit cell?
2.
Two, right? The corner atoms contribute to 1, similar to simple cubic, 1 by 8 times 8, and this particular atom is completely inside this unit cell. So the total number of atoms inside this BCC is 2. Fine. And let's look at FCC. This is your FCC. Okay. Let me just lower the, okay, this is the atomic dimension. How can I turn off the, okay, bonds, atoms. Okay, yeah. So this is how my face-centered cubic thing looks like. So 8 corner atoms and 6 atoms that are sitting at the center of the face. Okay. So what are the total number of elements, total number of atoms inside this unit crystal? Again, the 8 corner atoms will constitute to one atom overall inside the for this unit cell. And what about these face centered atoms? How many unit cell they are?
Three.
So one face centered atom are connected between, it is one interface, right? It is basically, you can see that half of the atom is inside the unit cell. So one particular atom of the face centered one, or face centered one, have half of its volume contribution to the unit cell. Similarly, we have 6, right? So that's how 6 times 1 by 2 gives you 3. Fine. Now for the last one, which is most useful for us, let us look at silicon. Okay, so this is how your silicon unit cell looks like. So silicon is what? From the face of it, let's ignore this inside atoms, okay, for the time being, okay? This is called diamond structure. So what are the atoms? It is a face-centered cubic, right? You can see that on each face I have one atom. But however, I have 4 more atoms inside the silicon, which is at a distance 1 by 4 of the body diagonal inside this, right? And this is the particular bond that we are looking at. So silicon will be bonded with 3 face cent. Let's say this is one silicon atom. So one silicon atom has 4 hands, right? So other 3 will be your face centered ones, and one is your corner atom. So it is similar to your, you have studied methane, right? CH3. So there you have seen this, right? How your 109.4 degree comes about. This is the exact same thing. Then the question should be, how in bond model, or let's say the question should be, we generally draw in the bond model as if my silicons are connected like this, right? We always draw it like this is the 4 silicon that is connected. Do you agree or not? This is how we look at it, right? At the bond model, that one silicon is connected to the adjacent 4 things. So what does that mean basically? So let me just show you how you can visualize that. So I need, yeah. So this is the crystal. So how do I show that to you? Okay. Yeah. So it is not aligning correctly. Yeah. So if you see in one plane, right? If you see in one plane, you can see that from a particular rotated point of view, you can from the top view, you can construct the exact bond model that we read in class, right? It is not that if this particular silicon atom is bonded with this is just a pictorial representation. How actually silicon atoms are bonded, if you just take the 3D view, you will see that the silicon is bonded like something different. So whatever is being seen in the front top view is quite different, right? That is just for the notion of understanding. Okay. So moral of the story is use this tool to get a feel about how the crystal looks like. Okay. You can increase the size of the atoms. You can check for Miller planes and so on. You can turn on Miller planes. Okay. And you can see that for this particular Miller plane, how many atoms are there. For example, let's say for this particular, this is one Miller plane, 0 1 0. Then I can have 1 0 1, then I can have 1 1 1. So how many atoms should be there? You can move this plane, you can move this plane up and down to check how many atoms lies in the Miller plane. So these Miller planes are important because through along these planes you cleave the material. Okay. Anyway, so that is this I'll share in your description of the window. Let me just share my screen again. How do I do that? Yeah. So basically, you should use that tool and get a feel for how the crystal actually looks like. There are a lot of options about looking into how many unit cells are there, what are the bases and all. Whatever you read in textbook or lectures, you can use that tool to visualize. Okay. So visualization in our domain is very important because we do not know how the MOSFET looks inside, because we do not have the access of transmission electron microscope or scanning electron microscope all the time, right? So as far this question is concerned, so we have seen that simple cubic has 18 into 8 1 atoms, FCC has 6 into 1 by 2 plus 8 into 1 by 8 has 4 atoms, and this body centered cubic we have 1 atoms inside plus 8 atoms at the corner. So we have 2 atoms inside the unit cell. Fine. So use that tool. I'll keep it in the description of the YouTube video so that you can use it. So yeah, another material, it is not getting deleted. Anyway, so another material is your gallium arsenide. Okay. So gallium arsenide has a zinc blende crystal structure which is equivalent to face-centered cubic lattice with 2 atoms per lattice point. Okay. In the same tool, you can also view zinc blende structures as well, right? Gallium arsenide, for example. Assume a lattice spacing of this. How many numbers of atom per cubic centimeter are there in a gallium arsenide? So what do they ask us to find out? The atomic density of gallium arsenide. Fine. So it is mentioned that it is similar to a face-centered cubic atom. So in face-centered cubic atom, I'll have atoms at the corners, and then I'll have atoms at the faces, right? But what is mentioned that it has two atoms per lattice point. That means per lattice point in a macroscopic picture, you will have two atoms each. So what are these two atoms? These two atoms are, one is your gallium, another one is your arsenic. These two together called basis. So in our case, basis is equal to 2, and it is mentioned that it is face centered cubic, right? So number of atoms in a gallium arsenide unit cell is how much?
8.
That is 4 for the face centered cubic and 2 for the basis. Fine. So 8 atoms are there in a volume of 5.65 into 10 raised to minus 8 whole cube centimeter cube of volume. I have just converted angstrom to centimeter cube. Okay. Angstrom to centimeter is 10 to the power minus 8. Angstrom to meter 10 to the power minus 10. Then they want us to find out in 1 centimeter cube number of atoms in gallium arsenide. That will simply be your 8 over 5.65 cube times 10 raised to 24. Okay. And this will come out to be, it has to be something between these two. You can just check 8 divided by 5.65 cube will turn out to be 4.4 into 10 raised to 22 atoms per centimeter cube. This is how you find out the atomic density. Okay. Why atomic densities are important? Because once you know the atomic density, you know how much doping you can do in the material, right? For example, you will see that almost all the semiconducting materials which provides a band gap has a atomic density of the order of 10 to the power 22 per centimeter cube, be it gallium arsenide, be it germanium, be it silicon. Fine. These are the order of atomic density. So how much you can dope? You can dope it, let's say 4 to 5 order lesser. That means whether you are doping it with, for silicon, whether you are doping it with phosphorus or boron, that concentration cannot exceed your, let's say, 10 to the power 19 per centimeter cube. Otherwise, what will happen? It is like a, consider it as a liquid. Okay, you are doping it. It is basically solute and solvent, right? Once you keep increasing the concentration, then it start to become a colloid, right? Similar thing happens here also. Once you start to increase the doping concentration, it starts to form a alloy with the dopant material. So that is not what is desired. We want the semiconductor to be silicon or gallium arsenide itself. However, we want to change the property, that is your the free carriers at room at any given temperature a little bit more or less by doping it in a little bit dilute fashion, right? That is 4 to 5 order lesser of this atomic density. So that is where the atomic density comes into picture. Okay, so we'll see the cases of degenerate doping and all in the future sessions. Okay, for the time being, I'll request you to use that free tool and also use the tools available on the nanoHUB. Oh, those who are doing PhD, it will be very helpful for you. Most of the information are open source nowadays and you can get it there. Fine. So I think that's all for today. So next session we'll start with X-ray diffraction. Okay. So okay. I think let's stop it here today. Any questions you have?
No, sir. Thank you.
Okay, fine.